Azerbaijan and Armenia. It's a very nice country, and I think that we will have a chance to meet there in 1 or 2 years, because we have some negotiations with omics, and maybe one of the next World Congress of Pharmacology will be held in Tbilisi. So the topic of my speech, today's speech, will be the prospective therapeutic agents from Boraginaceae family, from some species of Boraginaceae family. Here is typical Boraginaceae species. You know them. I think it's comfrey, quite well known comfrey, and Amphusa baglas. These species are quite well known for a long time, but the main thing that strictly is that FDA prohibited the use of these plants because they were used as plant teas, but they contain very toxic, hepatotoxic pyrrolizidine alkaloids. Thus, the internal use of these plants is prohibited. But as I am initially a biochemist, I work at the Institute of Pharmacochemistry, and we deal with phytochemistry a lot. It was a very interesting finding about in 203, 204, when we examined the high molecular polysaccharide fractions of these plants, we discovered a very unusual compound there. Here it is. Polyoxy-1, carboxy-2, 3,4 dihydroxyphenyl ethylene. It isn't a polysaccharide. It's a huge polymer. Here is the common scheme of extraction. But what is interesting, we have used the method. Initially, we have dialysis, and by this method, we succeeded in completely abrogating these toxic pyrrolizidine alkaloids. We had, here is the chemical structure of this polymer, and on the right, it's synthetic monomer that a part of our group has synthesized in our institute for the first. You can see, if you deal with chemistry, that it's a derivative of caffeic acid. It's very clear, very close to it. So it was very interesting for us to establish which purposes, which pharmacological features can be explored further. Here is the slide where we can, where we showed that there are no pyrrolizidine alkaloids. Absolutely, it's abrogated. You can see here what was the solvent system. It's common system for alkaloids with early reagent in the UV light. It's so interesting. So the first one we tried to do was two essential common models for wound healing. First was excisional, mouse excisional wound, and the second was mouse skin burn model. Probably, as you are all pharmacologists, you know these models. Let's go for the results. When we did the initial ointment using this polymer, here we can see the dynamics of healing effects with control, you see here, and with our ointment. I'm sorry, it's another abbreviation, it's the same. You can see that the difference at early stage is very, very clear. And the estimation we are doing using ImageG software. It's very convenient. We can directly measure from the digital photography, plot it, and everything is okay. Here is the same on excisional wounds in mice. And now I want to say the following. Very often, healing properties of comfrey are associated with allantoin. You know it. But we did the following. We get ointments containing either allantoin, synthetic monomer, as I showed you previously, BMB, and combined ointment, which was allantoin and this polymer. You can clearly see the difference between combined. It was expected that it will work better, but the second one is pure polymer, biopolymer from these plants. You see that the healing period is almost 5 delays of 5 days between control, and that's why we think that the main compound which is responsible for healing properties of comfrey is this polymer. It's the same in all in burn mounts. So if we compare, we are beginning to formulate this, how it may be done as a pharmaceutical dosage form. We did dressing ointment and we did dry ointment. So we are drying this extract almost, and then it is very lightly soluble. It's very good soluble in water. You can add 1 drop, and you have a ointment. Its shelf life is about 4 or 5 years, because itself it has antibacterial properties. So it's very, very, very convenient one. Here is, you can see the entire picture of our ointment, vehicle, and untreated control. In 15 days, we have almost complete healing here. So from this series, we can assume that maybe, as the structure of polymer, as you have seen, is very interesting. It has its molecular weight is about 1 million dalton. It's a huge molecule. It has a lot of hydroxy groups, and thus its antioxidant activities are absolutely clear. So, 2 of possible ways for anti-inflammatory and healing properties of this polymer is 1, scavenging of reactive oxygen species and inhibition of them and scavenging of. And the second is the inhibition of the pathway which converts hypoxanthine to xanthine. Both are, but we have some complications, and we'll talk about them. Then another study, it was very difficult, but we did it in collaboration with our American partners from Colorado University. They did the comparison of our polymer in 100 androgen-dependent and androgen-independent prostate cancer cell lines. And you can see that it is very clear effect. So its anti-cancer activities, always when we are talking about anti-cancer and when we have only in vivo results, it's quite, but they succeeded in vivo results, and you see that the xenograft is practical inhibition of tumor growth is about 40%. These two bars are represent the polymer from, you see, previously I showed you Symphytum asperum and Symphytum caucasicum. The chemical structure of these polymers is practically the same because the NMR spectra, IR spectra are the same, but we see that polymer from Symphytum caucasicum is much more effective. We don't know why. Another group, in collaboration with our Spanish colleague, Professor Vidalona Glocha, they showed that the same effects, anti-adhesion effects, is also present in our polymer. You can see here abrogation of adhesion, so this compound prevents metastatic development of tumor. And finally, we did a short investigation on drug-induced leukopenia in mice caused by cyclophosphamide. And here we see what is what is interesting here. You see that these three bars are actually polymers from roots and leaves, but this is synthetic monomer. Its activity is much less with than the natural polymer. So for today, we have established these main paths of activity that we want to develop furtherly. Here we can see the publications that were done on this polymer in cancerogenesis, in National Academy of Sciences Bulletin of Georgia, in pharmaceutical chemistry, and so on. Nowadays we have completely, not completely, but almost finished preclinical, so-called preclinical stage, and we are going to begin clinical, but we have something. This is my team, my colleagues from, you can see, from Georgia, from our institute, from the pharmacy department of our Tbilisi State Medical University, from Vizcaya, and from Denver. Of course, all of us know that science is money now. That's why special acknowledgement for CRDL Global Foundation from USA, Georgian Research and Development Foundation, and Shotarovsky National Foundation grants. And thanks to this foundation, now I'm here, because it supported my travel here. So that's all, but not at all, because I want you to show one more. What is the challenge for us? As we are here at the conference, maybe I can share our dots, and you can help us. It is, we are always open for collaboration. You can have, if you wish, all reprints of these articles. But the main thing is that if we compare synthetic monomer, natural polymer from Bagalas and from Anhuza, we saw the difference. I'll show it now to you. I have time still? Yeah. Okay. So, you see what's the difference between polymers obtained from Bagalas and from comfrey. In comfrey, all groups are hydroxy. In Anhuza, some of groups are methylated, here at carboxylic group. The activity here is much more less than in non-methylated polymer. In monomer, we have no methylated functional groups. And now, I didn't present this result because this study is in process, but we succeeded in obtaining oligomers. But the difference is that during the synthesis, all these groups should be closed and they are demethylated, and these oligomers have no activity. Now, what is the main challenge for us? To start any clinical trials, you must prove that your substance, your compound, is chemically pure. When we analyze the polymer, we see that we have some residues which cannot be deleted or removed by any known chemical reaction. Acid hydrolysis, base hydrolysis. That's why now we have an approach to try a fermentative hydrolysis. Maybe it will work because you understand that it is possible for a molecule that is 1 million Dalton to penetrate any barrier, but it actually works very active. So, if you have some idea, we are open. And once more, thank you very much for your attention.
Thank you very much for your interesting talk. Somebody has any questions?
Yes.
Did you try it on any other animal models only, or you tried it only on rats?
You mean anti-cancer?
No.
Wound healing. You see, it's a very interesting story because this crude plant, macerated, is very, very widely used in folk medicine in Georgia, especially in mountains. We had to use approved animal models just to approve this folk. No, we didn't. I tested it on rats and mice, but it's very difficult to approve dog studies because our ethics committee is quite, as always. So so these are only small organs. But in our laboratory, we always have an ointment. And even heart, some person, it's ready and in 2 days. I can tell you one story. My late mother had diabetes, and he was very badly burned by boiling water. And I had this at home. And I didn't believe it myself, but in 10 days, it was completely healed. So, it works, but how it works, we didn't know yet. So, thank you. No. It was hydrophilic. That's an advantage because it's water soluble. So we have especially we choose hydrophilic base. It could be washed completely in seconds. It's very convenient in case of baths because lipophilic like petroleum or so and so.
Yes, and in your formulation, did you use any precutaneous enhancer for absorption? No. Because the weight is very high, so to cross the skin it will be very difficult.
That's what
you can use precutaneous enhancer for absorption. It will be used like urea, ozone. These materials will enhance your absorption, and you can test these in the France cell diffusion. Also, you can take skin in the France cell diffusion and tested the absorption or precutaneous absorption of the drug from outside to inside.
So right now we have a PhD student now in our lab, which is working directly as what you are talking about. He has a France cell and he is now trying to
measure the precutaneous absorption.
Yes, because we didn't yet focused on finished formulation. Because if we don't approve the exact mechanism, nobody will approve such a drug.
Yeah,
of course.
Yes.
Thank you.
Yes.
Suggestion to this.
What?
I have small suggestion on your presentation
Yes.
on this stuff or chemical what you said. Such a huge molecule, it's impossible to expect to get diffused
Yes.
in the skin.
Yes.
Whatever the possibilities, whatever you try to manipulate it. My guess is, if it has got the ability of getting swollen,
Yes.
swelling factor, or it has got the ability of attracting the moisture, keeping the wool, especially the burn wool's moisture, the moisturing of the wool promotes epithelial cells migration. Maybe it's
Maybe.
sticking onto the wound. Maybe it's hydrating the moving cells, especially the epithelium. And most the bone wounds will have to heal at the end by epithelialization, less by contraction. Perhaps could be a thought we can think about.
So
Its ability to swell, ability to attract or keep the wound moisture. If we can assess its ability of getting hydrated and getting swell. And stick on to the local the open wounds.
Yes. Thank you very much.
Thank you.